Cambridge, England, where the likes of Newton and Darwin launched more than one scientific revolution. A controversy in 1968 also started here. It was in the Cambridge suburbs that the antennas of the Mullard Radio Astronomy Observatory picked up some bizarre signals. Anthony Hewish is one of the discoverers of those signals.
There was one in particular which my student Jocelyn pointed out, which was a little bit unusual.
The perceptive graduate student Hewish refers to was Jocelyn Bell. Day in and day out, she was studying radio waves from outer space.
And so I was looking for sources that twinkled, that varied. And rather to my surprise, I found something that looked a bit like a twinkling radio source, but was not exactly like it.
This is the actual record of Bell's observations. Usually there were hardly any undulations, but on this day, she detected some regular pulses. The regularity of the intervals is indicated by the arrows, and the signals were strong. This was a first. It looked artificial, unlike any natural phenomenon.
Crazy. Totally unlike anything astronomical. Never been seen before. Probably impossible. Pulse, pulse, pulse.
The pulses continued the next day, and the next. The exact same spacing. Close analysis revealed a period, or interval, of exactly 1.34 seconds. It was amazingly precise.
My immediate assumption, as a radio astronomer who's been in the game for several decades, is that it's some radio interference. Somebody is generating a signal somewhere.
Suspicion fell first on the spark plugs of passing motor vehicles. But testing found that an engine spark plug could not produce so regular a pulse. Next, they considered radio waves from nearby observatories. Perhaps they emitted radio waves during the course of their observations. But all the observatories they asked denied the possibility. Third suspect, the moon. Radio waves from sources on Earth might be reflected back to Earth by the moon, but the pulses were coming even on moonless nights. They considered ships' radars, arc welders, and amateur radio operators, all to no avail. Finally, they found proof that the signals were in fact coming from outer space.
The stars take 23 hours and 56 minutes to go round and come back to the same spot in the sky. Not 24 hours. They get 4 minutes earlier each day. And this object was moving like the stars. So it's either something very, very curious or it's stellar.
And here we have this signal. It looks quite unnatural. Was it an intelligent signal from outer space or not? That thought had to be taken seriously. someone started to use the name Little Green Men. I'm not sure if it's this recording or not. Yes, there we are. Someone, you see, I think that may be my writing, has written Green Men on the record.
Could Hewish and his associates prove a sentient alien source scientifically? It occurred to them that such a source most probably resided on another planet.
I think if you have alien intelligence, it's likely to be on a planet which is in orbit about a star, and that orbital motion could be detected.
Hewish thought as follows. Aliens are unlikely to be living right on a burning star like the sun. They would be living on a planet orbiting that star. And there was a perfect way to test whether the pulses did or did not come from such a source. Anything moving will give off sounds or radio waves of varying periodicity. For example, the sound of an approaching train will get higher. As the train approaches, the spaces between the sound waves it emits become shorter. That shorter cycle gives it a higher pitch. By the same token, as it pulls away, the spaces between sound waves get longer and the pitch lower. It's called the Doppler effect. So if those pulsing radio waves were from aliens on a planet in orbit about its sun, the space between pulses should grow longer as the planet moves farther from Earth. And as it moves closer, the spaces should get shorter. If this was the pattern, then one might indeed conclude that the signals were being sent by aliens.
This was around about December 1967, I was doing that work. And after 3 weeks, I could detect no orbital motion.
If the signals did not originate from a planet in orbit, then they did not come from an alien life source. That meant they had to emanate from a star. But what sort of star could send out these regular pulses? The mystery only deepened. It was then that they discovered a second, similar pulse, and it came from a totally different direction. The next day, they found a third, and almost immediately, a fourth. The objects emitting these bizarre signals were all over the universe. The mysterious objects came to be called pulsars.
But there was considerable surprise and interest in this result, and word went round the astronomical community very, very quickly about this surprising result.
And the whole world knew about it. And of course, every radio telescope that could point in the right direction looked at these pulsars.
A new celestial body emitting a mysterious pulse. What could it possibly be like? Pulsars were a strange new celestial body. A clue as to what they were like came from an unexpected source. 30 years before the discovery of the pulsars, a genius of an astronomer posited the existence of a fantastic type of star. In 1934, the Swiss astronomer Fritz Zwicky made certain theoretical calculations about the final stage of a type of giant star. When the giant star uses up its fuel, it erupts in a massive explosion called a supernova. After the explosion, what's left is an extremely small star. Furthermore, this small star is of a most peculiar kind. According to Zwicky's calculations, such a star might have the mass of our Sun, but a diameter of just 10 kilometers. The star would be composed exclusively not of ordinary atoms, but of particles called neutrons. So could the pulsars be the neutron stars predicted by Zwicky?
Stars, neutron stars, can rotate fast enough and produce directed radiation so that what you're looking at is essentially a lighthouse, like a terrestrial lighthouse.
Neutron stars have magnetic fields. The stars rotate rapidly, all the while emitting electromagnetic radiation, including radio waves. Like the light from a lighthouse, these radio waves will seem to pulse with every revolution. The neutron star was a winning candidate for the pulsar. If a radio telescope could detect those pulsing radio waves amidst the remains of a supernova explosion, then it would be clear proof that the pulsar was none other than the likely product of that supernova explosion, the neutron star. Telescopes were pointed to the Crab Nebula in the constellation Taurus. The Crab Nebula is formed of the remnants of a supernova that occurred in 1054. Ancient texts record that supernova. It was so brilliant that it could be seen even in the middle of the day. The Crab Nebula is some 10 light-years across. That is vast. It's 600,000 times the distance from the Earth to the Sun. Astronomers around the world are surveying it closely, believing that somewhere in these remnants of a supernova, there must be a neutron star. But no one has yet found a pulse. Perhaps the pulsar is not a neutron star after all. The Jewel of the Caribbean, Puerto Rico. In Arecibo, in the western part of the island, is situated a gigantic structure, the Arecibo Observatory. With a dish antenna 305 meters across, this is the world's largest radio telescope. Compare that dish antenna to a baseball stadium. The stadium fits in with room to spare. This giant radio telescope was used to search for a pulsar in the Crab Nebula. But even this telescope could not find a pulsar there. Richard Lovelace of Cornell University spent 8 months at Arecibo, observing the nebula. Why could a pulsar not be found in the Crab Nebula? Lovelace consulted with his colleagues. One theory emerging from their discussions was that it was there, but with a much shorter period than expected.
We should look for much shorter periods, because in fact the the pulsars found by Hewish and Bell, those were 1 second period, and one of them is a quarter of a second.
So Lovelace and his colleagues developed an analytical program to identify pulsars with merely 1/5 the period of most of the Hewish and Bell pulsars. On November 9, 1968, after Lovelace had completed his Gallup computer program, he focused Arecibo's giant spherical antenna on the Crab Nebula. Gallup worked splendidly, capturing and analyzing radio waves in rapid succession. Here are the computational results. Pulses were assigned number values in order of magnitude from 1 to 9. The strongest pulses of all were labeled X. And here is the much sought after X. Detailed analysis showed that this pulse from the Crab Nebula occurred at an interval of 0.03 seconds. That is a mere 1/40th of the pulsar periods initially observed by Hewish and his associates. The reason this pulsar had not previously been detected in the Crab Nebula was because the star producing it was spinning so fast, yielding such a small period. The Gallup program had scored a great coup.
It was really a turning point in the ideas about pulsars. So it became absolutely clear they were rotating neutron stars. There was no doubt about that.
Discovery of a pulsar in the Crab Nebula was the confirmation that all of this was fitting together, and we understood it properly.
In 1999, the Subaru telescope at the summit of Mauna Kea in Hawaii was aimed at the Crab Nebula. Observe the object indicated in the middle. Here it is in slow motion. Something is twinkling, flashing, unlike any of the stars around it. A pulsar. And it is indeed a neutron star, the remnant of a supernova. The strange object predicted by Zwicky had finally revealed itself. So the pulsar is a neutron star. It is the result of an exceptionally turbulent process. A giant star, 8 to 20 times the mass of our own sun, reaches the end of its life. It explodes as a supernova. In the middle of it all, the atoms that make up its matter are subjected to tremendously violent forces. The orbits of particles disintegrate. Electrons and protons fuse together, creating neutrons, which rapidly condense in volume. What finally emerges is a ball of neutrons a mere 10 kilometers in diameter. A neutron star is born. The spinning energy of a giant star, more than 8 times the volume of the sun, is now concentrated in this tiny object, 10 kilometers in diameter. So the neutron star revolves at fantastic speed. And with its magnetic field, the neutron star sends out pulses of both radio waves and light. This is the mysterious object, the pulsar.
Professor Anthony Hewish, the discovery of pulsars, for which you played a decisive role, is a move
For his
not
role in the
standard
discovery of the pulsar,
of how
Hewish was
in
awarded the
recent years
Nobel
our
Prize in
knowledge of the
Physics in
universe
1974.
dramatically extended.
Further research revealed even more, that the pulsar was responsible for a stupendous phenomenon that went beyond anyone's imagination. Stimulated by the discoveries of Hewish and Bell, astronomers all over the world are using radio telescopes to look for pulsars. Parkes, Australia is home to a scientist known as the world's #1 pulsar hunter. Richard Manchester. He's been using the Parkes Observatory to search for pulsars for the past 4 decades.
Parkes, it's a big telescope, but by world standards, it's not huge. There are radio telescopes in other parts of the world, in Europe and North America, which are bigger. But we've found twice as many pulsars as all of the rest of them put together. And we're pretty proud of that. So.
The telescope is located in a natural setting, with more kangaroos than humans passing by. There are almost no artificial radio sources nearby to contaminate observations of the universe. And given its location in the southern hemisphere, it has a great view of the center of the Milky Way. All this makes the Parkes Observatory the perfect place for pulsar hunting. Manchester also has a special device here. It's housed in a white box as large as a 2-story bungalow, positioned above the reflector. This will be a rare look inside the box. It takes 10 minutes to climb a 50-meter ladder to the white box.
So this is the multi-beam receiver. It has 13 beams. You can just see the feed horns through these panels.
Each of the 13 elements in the array collects radio waves from a different direction. A single receiver can cover only one region of space at a time. But Manchester and his team have developed an array of 13 receivers. This multi-beam receiver can observe 13 areas at once. Once the multi-beam receiver was introduced, pulsar identifications increased dramatically. Manchester's team soon found more than 1,100 of them. Thanks to the efforts of astronomers around the world, that number has reached roughly 2,000. If we could see pulsars with our own eyes, they would liberally populate the night sky. It has become apparent that pulsars, that is, neutron stars, are quite common throughout the universe.
6, 5, 4, 3. We have a go for engine start. 0. We have booster ignition.
In 1999, the Chandra X-ray Observatory was launched into Earth orbit. Earth is constantly bombarded by X-rays from distant parts of the universe. Ground-based telescopes, however, are hindered from observing them by the Earth's thick atmosphere. That is the advantage of basing a telescope in space, where there is no such interference. Chandra provides an excellent way to observe the remnants of a supernova. We'll look at a portion of the constellation Cassiopeia. There's that famous W shape. And off to one side is a supernova remnant dubbed Cassiopeia A. This is an image of Cassiopeia A, taken with visible light. And with visible light, that's about as good as it gets. With Chandra, however, it looks like this. Gas clouds enveloping a neutron star that is fiercely emitting X radiation. What does an analysis of their composition reveal? This shows the presence of silicon. The redder the area, the more there is. The distribution indicates the extent of the supernova explosion. This is calcium. And this is the distribution of iron. Elements such as iron and silicon are produced by supernovas. Next, we'll use Chandra to search for a pulsar. This nebula lies in the constellation Sagittarius. A pulsar in its midst flashes with exceptional luminosity. Ringed by gases, it's understandably called the bullseye pulsar. This supernova remnant is in constellation Vela. A pulsar has been detected here. The nebula has an odd, tail-like protrusion. This nebula has some pointiness to it. It also has a pulsar, here. Gases expelled by a supernova normally expand outward in a spherical fashion, but collisions with surrounding gases have produced these strange angles. This nebula has a long, long tail. And at one tip, a pulsar. The gas cloud is 4.2 light-years in length. Measurements show that the pulsar itself is not going anywhere, so this long tail is a mystery. This nebula has been called the Cosmic Hand.
The nebula almost looks like my hand here, with the pulsar sitting here. There are finger-like structures reaching up here. There's a thumb-like region over here. And we don't know why it looks like that. I think most of us just smiled and looked at it and said, well, this isn't going to be easy to explain.
The pulsar is located at the heel of the palm. The hand seems to be trying to grasp something. It's a broad palm, 150 light-years across. Truly, this cosmic hand is an awesome sight. Scientists find another structure to be even more astonishing, though. The Crab Nebula. Chandra can capture the X-rays it produces. What appears now is a mushroom shape. This is quite different from its optical image.
びっくりしましたね。非常に個人的にはとってもびっくりしました。
Koji Mori used the Chandra X-ray Observatory to study the Crab Nebula. He observed it continuously over a 5-month period. As he did so, he saw an awesome phenomenon he had no expectation of seeing. What attracted his attention was the ring of gas in the center. He imaged it at 3-week intervals and combined the results. It had moved. The ring is 1 light-year across. That's 60,000 times the distance from the Earth to the Sun. Yet on that gigantic scale, the ring suddenly enlarged.
光のスケールのサイズを見ているのに我々の実時間ぐらいで変化しているってことは当然これははっきり言って光のスピードの何分の1かぐらいで動いてないとこんなことは出てこないはずですからすごいもん見ちゃったなっていうところですかね。はい。
A ring expanding at half the speed of light. Why is the gas ring expanding at all? One scientist has tried to solve the mystery of this pulsar phenomenon by means of computer simulations. Shinpei Shibata thinks that the reason the ring is enlarging so fast is that the pulsar at its center carries an exceptionally powerful magnetic charge.
とっても強い磁石が宇宙空間で回転している、磁石が回転するととっても強い、発電機になるわけですね。
Shibata and his associates used a supercomputer at the National Astronomical Observatory of Japan to simulate the pulsar's environment. Then they set a pulsar, meaning a powerful magnet, spinning in that environment. That yields a vast amount of electrical energy, which in turn produces a huge quantity of particles. The particles are spun off by the rotating pulsar and flung out toward the periphery. The speed of these ejected particles has been calculated. It's 99.999,999,999% of the speed of light.
ほとんど光の速さで飛び出てくるんですよね。まるで嵐のような、これをパルサーウィンドとパルサー風というふうに言っています。磁石が回転しているっていうたったそれだけのことなんですけれども、それがあまりにも強力な磁石であまりにも強いと中から電波が出てきたり、あるいはガンマ線も観測されてるんですね。ガンマ線が出てきたり、粒子が高エネルギーの粒子が吹き出てきたり、プラズマの嵐のようなものが作り出されるということが分かってきたんですね。
The pulsar wind blasts out at light speed. At those fierce speeds, the pulsar wind pushes surrounding gases outward. This rendering of the pulsar is based on the latest research by Shibata. And so we take an imaginary journey into deep space, to the Crab Nebula. We plunge into the nebula, greeted by a fearsome particle storm with winds reaching half the speed of light. It's still 1 light year to the pulsar. We can see the ripples spreading out. The pulsar is now 1 billion kilometers away, and now we can see the lighthouse effect. The source of that flashing light is the pulsar. Finally, the pulsar itself, a shimmering ball of neutrons, just 10 kilometers in diameter. Its gravitational force is so tremendous, all bumps and dips are leveled out. The surface gleams like a mirror. It even reflects the spaceship. It's simply amazing that such an object exists. Seen close up, the pulsar can only be called a wonder of the universe. The latest research has revealed that pulsars are also a source of a certain element of particular interest to humans. It happens during the most violent explosions known to occur in outer space. Thomas Janka and Shinya Wanajo are pursuing this matter by creating computer simulations of violent collisions between two neutron stars. First, Janka creates the neutron star collisions.
The two neutron stars orbit each other in very close distance. You can see that the distance between the two neutron stars is a bit smaller already than the diameter. And then the two neutron stars actually finally approach each other with violence and merge into one big blob of matter.
As soon as they collide and merge, the two neutron stars are enshrouded in a misty shell of particles. These are neutrons, shed by the neutron stars.
And the jet in the end, at large distances, radiates a gamma ray burst, which we see as the brightest flash observable in the universe.
The two neutron stars approach one another rapidly. Finally, at 30% of the speed of light, they collide and merge. At that point, a huge quantity of neutrons is released, along with a huge amount of energy, causing a gigantic explosion. The biggest explosion in the universe, a gamma ray burst. Wanajo believes that this is when various forms of matter emerge from the cloud of neutrons released by the explosion. They say that it is actually rather easy to envision the phenomenon of neutrons producing other matter.
これが元素の中心にある原子核だとしましょう。原子核というのは電気を帯びた陽子、これと電気を持たない中性子、これらの集まりでできています。
The neutrons that spread about at the moment of impact carry a neutral electrical charge, so they can combine with other matter easily. They offer no resistance. As more and more neutrons attach to a given nucleus, the nucleus grows larger and larger. Wanajo calculated the type and quantity of elements created at that stage. Consider what happens during the first 0.3 seconds after the explosion. The line extending towards the upper right of the graph indicates the volume of neutrons combining together. Heavy elements appear in a flash. .01 seconds after the blast. The neutrons, as they combine, begin to form heavier nuclei. Large quantities of neutrons whiz about, creating elements such as iron and silver. At 0.3 seconds after the explosion, more neutrons get added. When they reach a certain mass, the nuclei stabilize.
実はここでこの流れが遅くなっているポイントがありまして、ここで、非常に多くの物質が作られているのが分かります。これが金やプラチナなんですね。
So the collision scatters vast quantities of neutrons about, and in very short order, they produce gold. So how much gold does the collision of those two neutron stars produce? And how does it get scattered about? This is a computer graphic rendering based on those calculations. All those neutrons have produced a vast quantity of gold, which is then dispersed through space. The quantity of gold produced at this time is equivalent to triple the mass of planet Earth. Wanajo and Yanka say that if one goes back far enough, one could trace Earth's gold also to collisions between neutron stars.
At least the neutron star mergers seem to be a good candidate for the main producers, for the origin of most of the very heavy elements like uranium and gold.
Collisions between neutron stars, happening far away and long ago. The gold we ourselves handle was created by the largest collisions in the universe. During the filming of the work done by Pulsar hunter Richard Manchester, an unexpected discovery was made. Coffee cup in hand, he begins his observations for the day. Manchester knows a number of regions where pulsars are relatively likely to be found. He targets one of them. For 30 minutes, he directs the 64-meter antenna at one star in particular. That's when it happened.
Oh, look at that.
Yep.
That's a binary.
Well, now let me just. I turned off period derivative search.
Is this binary star the kind that produces gold?
Straight. Although
There's a curvature.
There's a curvature, yeah. Another one.
Great. Very good.
Yeah.
That could be an interesting source. What's the period?
So, 123 milliseconds.
123. So it could even be a double neutron star system.
So 3.4.
So that's pretty amazing. Wow.
Not a bad haul.
Pretty good.
Yeah.
And we only know of 10 or 12 of these systems out of the 2,000 pulsars that we know about. And so finding another one would be very exciting.
The two neutron stars in a binary system will eventually, it is thought, approach each other and collide. Along with one of the greatest explosions in the universe, the result will be an increase in the amount of gold in existence, an increase equivalent to several times the mass of our entire planet. Today as well, pulses from afar are reaching our planet. Pulses that led to the discovery of neutron stars, spectacular celestial bodies. The pulsating neutron star, or pulsar, is the strangest object in the universe, and one deep